If I were paying somebody to do this switching regulator layout and it came back to me looking like this, I would not accept it. I would demand that it be redone. And frankly, if I was doing this design for a client and I showed them this, they wouldn't accept it either. Hello everyone, welcome back to Altium Academy. I'm your host, Zach Peterson. Today, we're gonna be doing something special where we compare a human-designed PCB layout versus an AI-designed PCB layout. Now, this topic came to me from a recent LinkedIn post, and if you follow me on LinkedIn, you know that I love to complain about AI. Maybe not complain, but actually just point out the shortcomings when used in some specific applications. But regardless, we're gonna be taking a look at a PCB layout that came to me from a LinkedIn post. And in this post, we had a human-designed PCB layout and an AI-designed PCB layout. We're gonna look at them both side by side, see what the AI did right, see what it got wrong, and how it compares to the human design. Both AI and a human worked on the same PCB design, and they have the same board outline, same components, same everything, and we're gonna take a look at how the layouts turned out. Now, this particular PCB came to me from a LinkedIn post from Mattia Fiumara, and Mattia works as a tech lead at a company called Agurotech. Now, I don't know if Mattia actually does PCB layout for a living, but he does like to post about it, at least recently he does, and this is the post, as you can see on screen. And in this post, he asks, which PCB layout is AI generated and which one is routed by a human? If they realize the same functionality, does it even matter? Well, I think that's a fair question, but there's a lot more that goes into a PCB that you actually turn into a real product than just turning on and interpreting signals, but we'll get to that later. Now, down at the bottom of this post, we can see two images. Here we can see we have image number 1 and we have image number 2 of the same PCB layout. And he asks right up here at the top of his post, which PCB layout is AI generated and which one is routed by a human? Now, I thought Mattia was trying to bamboozle all of us by showing us two images of PCBs, both of which were routed by AI. And as it turns out, that wasn't the case. One of these PCB layouts was actually designed by a human, and that human's name is Zach G. Now you can see right here, we have Zach G posting in the comments section, and he writes, I am the author of this post that was ripped without being cited. Just to be clear, the entire purpose of this was to demonstrate how horribly lacking AI is at doing anything meaningful in the PCB design space. It is not even at the step of writing hello world to make a coding analogy, and I'm skeptical the current approach is even capable of progressing beyond that. AI-RL, referring to reinforcement learning, is only as good as the data and the quality of the feedback. Well, Zach, I agree with you 100%, and I apologize for leaving such a snarky comment after succumbing to the rage bait that is this post. But I do want to leave it up to the viewers to decide which of these PCB layouts is better, the AI version or the human version. Well, lucky for us, I have both of those PCB layouts loaded up on the computer right now. Let's go ahead and jump into Altium and take a look at them both side by side, and I'll let you, the viewers, decide who did it best, AI or a human. So here we have the human-designed PCB layout on screen. This is a 4-layer board, and it is in the signal, ground, power, signal layer stack. And you can see here in 3D that we have topside placement has all of the components, and then we have some through-hole connectors along the top and bottom side. We also have a couple of pin headers here for our battery input and for our ground. So first thing I want to take a look at is just some of the basic stuff with setting up the routing and some of the feature sizes. What type of feature sizes are we working with? Well, here you can see that if I turn on my filter and I select some of the traces, we're basically dealing with 6 mil traces. And then if we select some of these vias, you'll see here we're dealing with 12 mil hole size and 25 mil pad diameter. So those are both really good starting points for this type of board. You don't really need to go smaller than that. You don't have high density BGAs, you don't have high density placement of components, so there's really no reason to go to smaller feature sizes. And the reason is that going to smaller feature sizes can increase your costs when you go to fabricate this. Next, the layout was done with solid internal planes. You can see here we have a solid ground plane, and then we have a solid power plane. Now, in these types of designs, I would have preferred that layer 3 be a solid ground plane. You generally don't need to have a solid power plane in these 4-layer designs. However, it looks like from an initial survey that the use of the power plane was basically done correctly. You do have stitching vias nearby a lot of these signals as they traverse from the bottom layer to the top layer, and that does help to maintain signal integrity by maintaining a return path, and then it also does help suppress emissions. Also, some of these lines, as you can see here, they are basically just DC lines. For example, this battery sense line. Some of them are also very low speed lines, such as these UART lines, and so they aren't really going to create a lot of risk of emissions anyways. If we had much faster interfaces, like for example, USB lines, we would want to keep all of that on the top layer close to the ground plane, or if we did route through the entire Stackup, it would be a good idea to include more stitching vias on that via transition. Some of the things I did notice in this design, I noticed that there were 6-pin headers that were used for the input power to connect to what looks like a battery. Here, if you do have these 6-pin headers, you do get really high current handling capability, but of course there could be some more compact 2-pin connectors that would allow you to have the same level of current handling without having to have these input and output side headers on each edge of the board. That's just a personal choice or more of an engineering choice. Also, it's kind of a mechanical or form factor choice, so it's probably what I would do if this were my design, but I don't think it really impacts the functionality. Also, you can see here that we're using some pretty thick copper to route this from that battery input over to our first input regulator, so I say good job on that. Next, if I go back to the top layer and I take this out of single layer mode, I'm doing just a quick scan of this PCB, and I'm looking for any silk screen that might be falling on pads. Just a quick survey shows that this surface layer was cleaned up very well. You can see that we have the pullback between the copper that is on the top layer and the board edge, so good job on that. Also, the copper pour on the top side and the bottom side also helps to provide a ground reference for these signals on the bottom side, which is also helpful for EMC. Next, I want to take a quick look at the Stackup. Here you can see in the Layer Stack Manager that we've defined some thicker prepregs on the outer layer for this board. So we have 11.5 mil of dielectric on the outer layers. And that's one reason that we might want to include that copper pour on the bottom side. This is something that I discussed recently with Dr. Todd Hubing on an episode of the Altium podcast. So having that ground pour helps to provide that ground reference for these signals on the bottom side, whereas the signals on the top side have both the copper pour that's balanced on the top side and then the ground layer on layer 2. Finally, a few things I would change. I would have considered just removing all of the thermal attachments. The reason is that I generally put things through reflow. I don't do hand soldering. But of course, if you are going to do hand soldering, having the thermal attach is helpful. Next thing I want to look at is the ground pad connections on the bottom side of this LGA. Here, I would have bridged all of these together using a solid piece of copper and then connected it to the surrounding pour. And then I would have interleaved all of these ground vias in between all of the solder pads in this footprint. However, doing it this way is probably just fine as well. There's a lot of ground vias surrounding this pad array, so I think you're going to get the same effect. Last point I want to bring up in this layout before we take a look at the AI version is the switching regulators. They are laid out very well. You have a nice tight placement for all of these components around these ICs, and that's going to be really important for helping to control noise. Also, it makes routing between these large components and the regulator ICs much easier, as you can see here in this part of the screen. And of course, when we run the design rule check, we get 0 errors. That is exactly what I would expect from someone who knows what they're doing when they're making a PCB layout. So now let's take a look at the AI version. You can see here we have the layers turned on, and let me zoom out so we can see everything that's going on in this view in the PCB editor. Now, first things first, you're all probably wondering what is all of this stuff above the PCB layout. And this is a whole bunch of rooms. Apparently there's 18 rooms defined by the AI above the PCB layout. Like, they're not even in the same region as the PCB layout. I have no idea why you need to have 18 different rooms defined in this PCB doc file. There doesn't seem to be any reason for it whatsoever. Sometimes when you have different schematics or different component classes or different groups of components where you want to apply specific design rules, you might apply those room definitions so you can control where those rules apply, but these were all auto-generated by AI, and I really don't see any reason for doing it at all. Next, let's zoom in here on the PCB just a little bit, and we can see a few things immediately. Here you can see that we have some design rule errors. We have a clearance constraint violation. Here we have another one on this mounting hole, and then we have another one right here on this component LP1. We have what looks like an unrouted net violation right here between L2 and this switching regulator component. And then we also have some clearance or feature size violations that are flagged right here on this connector. Right below this, we can see that we have some silk screen markings overlapping. We have silk screen falling on copper, and then we have some other unrouted net errors, as you can see right here between these two components. When I zoom out and we compare the placement of components in this layout versus the human layout, the placement is different. There are some components that are locked in place. For example, we have these switches down here, we have the SMA connector, and then we have a couple of these components along the top edge. So those components, as well as this central part right here, are all locked in place, but the rest of the components are all free to be moved. So before we start digging into some of those violations, let's take a look at some of the feature sizing that was used in this layout. Here you can see that the vias used are 8mm drill holes and 18mm pad diameters. Also, they don't really need to be that small. It's not that it's unmanufacturable, but in this particular layout, there isn't really a reason to use vias that are that small. Also, some fabrication houses will charge you more when you go to smaller drill diameters because of tool consumption, and that's especially the case if you were to take a board like this and bring it into volume production. Now, why exactly did the AI choose those specific feature sizes? Well, I don't know for sure, but if we open up the design rules, we might get a clue as to why. Here, if we look at the routing width rule, you can see that the preferred width is set to 4mm. If we look at the routing vias rule, you can see that the preferred via diameter is set to 8mm hole diameter and 18mm pad diameter. So that's probably why the AI chose to use those specific feature sizes on all of this routing. So like I said earlier, it doesn't necessarily mean that the board won't work or can't be manufactured, but that's one of those factors that you have to balance as a human who is designing a PCB to eventually be manufactured at volume. Now, as I close out of that window, the next thing I want to take a look at is some of the placement of these components, because in this view, you can already see what's happened with this placement. The placement has left an unrouted net error here between this inductor and this switching regulator. In addition, if we take a look at this switching regulator with U2 and inductor L1, you can see the routing with that boost converter. It uses traces when it should be using polygons. Also, you can see here that it uses this weird any angle routing, and I'm really not sure why, other than the fact that this placement is just really bad. Here you can also see some of the crazy routing decisions that the AI makes. Here you can see that we have a line coming off of one of the pads for this inductor, and this is on the boost SW net. You can then see here that this trace routes down onto the bottom layer and then has to route back up just to reach this pin for this switching regulator. You can see that the other placements of some of these parts around this switching regulator are kind of all over the place, and this of course creates risk of a lot of radiated emissions. If I were paying somebody to do this switching regulator layout and it came back to me looking like this, I would not accept it. I would demand that it be redone. And frankly, if I was doing this design for a client and I showed them this, they wouldn't accept it either. Now that's just this switching regulator layout for L2, but we can see similarly horrible layout for U7. It results in an unrouted net. Now this is despite the fact that if I really wanted to, I could actually take a via, drop it right here, and then route a trace on the back layer over to this pad, and then use another via to reach this pin on the top layer. So this route actually could be completed in the current layout, in its current form, despite how horrible the layout is. My earlier remarks apply to this section of the layout as well. If I were paying somebody to design this and they came back to me with this layout, I would demand that they redo it, and my clients wouldn't accept it either. Next, as we look around this layout, we see a lot of these any angle routing sections that make these really weird turns going between all the different components. You can see it over here near the inductor L1. You can see it in this region that we were just discussing. You can see it down here coming off of U2 and U3, and you can see it over here coming off of D4 going over to these test points. Now, one of Matthias' questions that he asked in his LinkedIn post was whether or not this routing or this layout would be functional. And a lot of this weird routing would actually be perfectly functional. But that's kind of beside the point. The point is that this weird routing arises because of really poor placement, and the poor placement creates its own set of problems that aren't dealt with routing. Also, this weird routing in some area creates other bad routing in other areas, which actually has rule violations and creates an unmanufacturable board. So the point I'm trying to make behind the weird looking routing is this. The weird routing is a symptom of a different problem, which is the bad placement in the PCB layout, and then it causes other problems, such as these design rule violations that you see right here near these mounting holes. Now, the bad layout decisions aren't limited to the switching regulators. They actually span all the way up to, for example, these components that should be connected near this USB connector, but for whatever reason, they've been placed farther away from the USB connector. So, for example, we have these resistors which connect to U8. And you can see here, U8 is actually an ideal diode. So if we just take a look here inside the schematics, we can see what U8 is. U8 is a diode array. This diode array is connected to both the battery input and the USB input, and it's basically being used for ORing. You can see here in the schematics that we have two resistors that are associated with this diode, but you can see here in the layout that they've been placed far away from the diode, and there's really no reason for it. Now, I would argue that because these components have been grouped together in the schematic, the layout should have known to also group them together in the PCB layout. Apparently, it did this successfully with a lot of the other components, but there's really no reason why it couldn't do that with these three components. If it did this correctly, it would have been able to avoid some of the funky routing that you see here, where we have all these extra vias and there's all this crossover between these signal lines that only exists because of bad placement. Next, let's take a look at the pad array on the LGA component. Now, just for reference, let's go back to the human design and let's take a look at this pad array here. So this pad array on the LGA is shown here routed together with thick traces, and then we have a lot of ground vias nearby connecting this back to the ground plane. Here in the AI design, we have traces that are being used to connect all the pads, but they just connect all of the pads together, what looks like almost in series, and then we have one single via that takes all of the current from all of those pads and then dumps it into the ground plane. There's plenty of room on this ground pad array to add a bunch of stitching vias around these ground pads and make multiple connections to ground rather than just having a single connection to ground. The same can be said for some of these other pads in this design. For example, you have a group of ground pads right here, and they're all bridged together with the same 4mm trace and then a single connection back to ground. As we look around this LGA footprint, we do see that some of the ground pads have their own individual connections to ground with vias, but it's only when they're separated from each other. Now, as we look around this footprint, you can see here there's a couple of other ground pads on this footprint that are connected back to ground using individual vias rather than being bridged together, which is probably the way you should do it for all these other pads. However, if we just look around here to the top side of this footprint, we see that we have three adjacent 3v3 pins on this LGA, and they're all connected individually with vias. Now, I don't know why the AI chose to connect all of these pads together and then connect them back to ground with a single via, but it decided to take these adjacent pads and split them up onto different vias. There's kind of no rhyme or reason as to why it's making these different routing decisions. This is one of the things that's kind of difficult about the AI tool that was used to route this board. It's kind of a black box and you don't really know why it makes the decisions it does. That makes it really difficult to give proper feedback and then apply updates to the PCB using the AI tool so that it can actually get the routing correct. Whether or not that changes in the future is going to be something that we'll find out over time. Now, the last thing I want to look at in this design is, of course, the DRC check. I want to look at the design rule report, and you can see I have it pulled up right here. Here we have 168 rule violations. Now, that's not as bad as some of the human designs we've seen come through for 1-minute design reviews, but, you know, it's 168 rule violations. You can see here we have 11 clearance constraint problems with a gap of 6 mil. So the AI should have easily been able to take care of this. Here we also have minimum annular ring constraints that are not satisfied. We also have those 2 unrouted net constraints that are picked up. And then most of these rule violations are actually really simple. These are silk to silk clearance and silk to solder mask clearance violations. Now, quite a few of these violations could be cleared up if we just change the default design rules, and this is another opportunity to apply AI in PCB design. That would be automatic generation of design rules for your PCB layout. Now that should be something that's really simple to do, because if you go into the design rules for this PCB and you right-click in this column, you'll see that there's an option to import and export the design rules. Now if you take that exported rules file and open it up in Notepad, you'll see that these rules files are formatted in human readable language. That means it should be pretty easy to develop an AI system that uses an LLM to automatically generate these rule files from human language. So maybe that's an opportunity for someone out there in the audience to make a very helpful AI tool for generating PCB design rules. Now obviously I have a lot to say about this layout and I could keep going for a while longer, but instead of doing that, I want to hear from all of you out there watching this video. Make sure to hop into the comments section and let me know what you think of this PCB layout. And if you're new to the channel, make sure to hit the like button, hit the subscribe button, leave your comments and questions in the comments section, and last but not least, don't forget to call your fabricator, folks. We'll see you next time.